And I'm only going to give you a single example of that. So here's the issue of problem spaces. I could have picked several other ones, although this was sort of probably the best one to illustrate it. This idea is so trivial as to be uninteresting to almost everybody I know. Okay? Which is to say it sort of says if you're going to do search, you ought to do it in a state space. State spaces, what's the big deal? We all know what state spaces are. They're spaces which have states and transitions between them. That's all that's to be said about it, except they're kind of a useful formalism. So what is a problem space? A problem space is a set of states and a set of operators from state to state, and you have a problem if they go from some initial state to any of a set of desired to one of a set of desired states by applying that sequence of operators. All seems fairly straightforward. But now look what's happened over time. In '57, when this idea first showed up, it was that a search space was the appropriate thing to do heuristic combinatorial search. That is, we were just discovering in AI that there was a combinatorial search problem, and that you had to kind of modulate that with heuristics, and that's why it wasn't called the problem space quite then. It was simply called the search space. That was the initial idea. By '65, this idea had transmuted into that is the space in which all problem solving occurs. That is, when you look at any difficult problem solving, it always occurs in some problem space. That wasn't clear up here at all. There were just some problems that were formulated this way. Okay? So that's a significant change. In a few years later, I can't quite pin down the date, the idea surfaced, the idea was finally understood that unlike simple little AI programs, real human intelligence has such a huge body of knowledge that its problem is that for any task it wants to do, it must select out a small arena in which to do this task, and it must get rid of almost everything else that it wants to do. So there is a deliberate limitation to an arena. And the problem space is the notion that relates to how the human limits the arena. Whether, in fact, it used it for search or not is irrelevant. There's this notion of limiting the arena because the human can do so many other things that it couldn't possibly, in some sense, consider all of them or bring all of that knowledge or ask about all of that knowledge. It's got to impose, and this is done deliberately, of course, so we can change that arena and work on a problem differently. By 1979, this notion had gotten enriched because it wasn't just problem solving. That should have been not the area, it should have been the arena again, in which the problem space was the organization in which all cognitive activity was supposed to occur, Okay, these are all hypotheses, of course, about the nature of human behavior, hypotheses which most of the rest of the AI and cognitive world is not paying much attention to. This concept is sort of getting deeper and deeper as it goes along. So that shift from just problem solving to all cognitive behavior, routine and otherwise, to be accomplished within problem spaces. It seems incredible now that all the way through this, one only talked about single problem spaces. And so the idea got changed in '83 with essentially the development of impassing and universal subgoaling and SOAR, to the fact that one now had multiple problem spaces, and that the relationship between those problem spaces was not implementation, but was a lack of knowledge in this problem space about how to do things would lead to the setting up of another problem space. And so that enriched the notion of the role of problem spaces in cognitive behavior. There was now to be a whole web of them. What is, I think, the biggest transformation occurred in '87, in which problem spaces all of a sudden turned out to be a least commitment program control construct. Okay? Let me try and explain that. It turns out that what you want in an intelligent system is not to commit yourself in advance to how you're going to control things, but to wait to the very last minute to assemble the knowledge right then in order to do control. And so if you separate all of control knowledge from all of the things you can do, the operators, that is a problem space. So here it is, having nothing to do with search at all, but being fundamentally a control construct. And the way we arrived at this actually was by observation of SOAR, in which, having been imbued with search all the way through this, we sort of looked at SOAR, and SOAR most of the time wasn't doing any search. And when you ask, well, what was the problem space doing all of that time, the answer was it was being this controls construct of delaying to the moment of action the assembly of control knowledge that might have been generated just a little bit before in order to do the control at that point. But we're not through yet. In 1990, which is sort of this is actually a little odd in time, but I'll just let it go. The idea that an intelligence system has the problem of how it formulates tasks out of nothing. Where do tasks come from? The programming world says a task comes because a human has a task and it puts that task into a program. Therefore, don't ask. You know, child, be quiet. Tasks come from humans. We don't ever have to ask how they come. But if you're talking about what is the nature of human cognition, you must say, how does the human who doesn't have a task arrive at that task in the first place? And it turns out that the problem space becomes a device for how to formulate tasks out of nothing, in addition to all of these others. And then the last one has a question mark because we know it's there, but it's totally undeveloped. The problem space is a generalized device for error recovery, which is to say that there I am in this problem space, which is a search space, and anytime an error happens, I am already embedded in a larger context in which I can consider alternatives. So that error recovery becomes a very different kind of situation than it is in most programming systems. That is an undeveloped idea, but I assure you it's there. So here's one simple construct. Yet over time, by nurturing it, it has turned out to be an exceedingly rich construct, and I assume it's going to go on. It's going to go on from there. There's a similar story that can be told for some of the others. I'm not looking at my watch anyway, but I assume I don't have time to talk about those. So let's talk about choosing the final project. The maxim here is choose a final project that will outlast you. My best example of this is an economist by the name of Fritz Machlup. Fritz was a fairly famous economist at Princeton, had worked in all kinds of areas in economics, had published in 1962 a book called Knowledge and Its Distribution in the United States, which was sort of trying to show there really was a knowledge industry, and from an economic point of view, you really ought to track the knowledge. Okay, you ought to characterize it and do statistical studies on it and so forth. When Fritz retired from Princeton at the usual retirement time, he said, what I want to do is to write an 8-volume study, which is going to have, it's like the Knuth issue, right? It's going to have a volume for every chapter of the previous book, which really treats this right. Okay? Now, as time went on, that got expanded to be a 10-volume study and so forth. And when Fritz had a heart attack at age 80, he was up to volume 4, and he clearly had succeeded in picking a project which outlasted him, and so he died with his pen in his hand, which is exactly the right way to die. Okay. So that's one thing, and the other maxim I would have you attend to is that everything must wait until it's time. Science is genuinely the art of the possible, and that's going to be reflected in this list. So SOAR seems like a typical final project, especially as you see it now, in which it's clearly going to outlast me. All right. Look what has to be done for SOAR. A couple of these we've done, but most of them we haven't. It's got to have the right architecture. It's got to learn continuously from experience. It's got to communicate with the external world easily. Okay, so that's some years from now. It's got to learn continuously from its environment, not just from its internal experience, which is sort of what it does now. It's got to live a long time, okay? Maybe not 10 to the 9th decision cycles, but 10 to the 7th decision cycles at least, okay? It's got to, people keep telling it, it's got to embody all of its tasks simultaneously. You can't build one source system for this and one source system for that. You've got to put everything in the same thing, because that's what's true of human cognition. It's got to become very large. It's got to have